Campi Flegrei has spent generations reminding southern Italy that silence is never the same as inactivity. Stretching across the western edge of Naples, this immense volcanic system appears, at first glance, to be an ordinary landscape woven together by neighborhoods, fishing ports, vineyards, ancient Roman ruins, and busy streets filled with millions of people living ordinary lives. Cars move through narrow roads, ferries cross the Bay of Naples, tourists admire centuries-old architecture, and restaurants overlook tranquil waters reflecting the Mediterranean sky. Yet every one of these familiar scenes exists within one of Earth's most closely watched volcanic regions, a place that has spent nearly 75 years delivering signals that scientists have struggled to fully interpret. Those signals did not arrive in dramatic fashion. They emerged gradually, almost patiently, through subtle movements measured over months and years rather than hours. Land that should have remained stable began rising by only a few inches before climbing several feet over the decades. Earthquakes that once occurred only occasionally became increasingly frequent. Ancient harbors built by the Romans appeared to move relative to sea level. Wells changed. Gas emissions shifted in both temperature and composition. Instruments installed by volcanologists recorded evidence that something deep underground refused to remain still. Each development, viewed on its own, seemed manageable. Taken together, they formed a pattern unlike almost anything observed at another densely populated volcanic system on Earth. Campi Flegrei, whose name translates to the burning fields, is not a single volcanic cone rising above the landscape like Mount Vesuvius. Instead, it is a vast volcanic caldera spanning approximately 8 miles, or about 13 kilometers across. The depression marks the remains of enormous eruptions that transformed the region tens of thousands of years ago. Those prehistoric events released astonishing quantities of volcanic ash, pumice, and molten rock, reshaping southern Italy and scattering volcanic material across much of Europe. Unlike the sharply defined silhouette of a classic volcano, Campi Flegrei hides its immense structure beneath towns, roads, coastlines, and farmland. The caldera contains more than 24 volcanic centers, craters, and vents, many of which remain visible today as hills, lakes, fumaroles, and steaming fields. Solfatara, perhaps its most famous geothermal area, constantly exhales sulfur-rich gases through cracks in the earth, offering a persistent reminder that intense heat remains close to the surface. For centuries, local residents have lived alongside these visible expressions of volcanic activity. Steam rising from fumaroles became part of everyday life. Warm springs attracted visitors dating back to Roman times. Legends, myths, and historical accounts intertwined with natural phenomena that people could see but rarely understood. Modern science eventually revealed that these geothermal features represented only the surface expression of a far larger volcanic engine operating several miles below. Deep beneath Campi Flegrei lies a complex plumbing system where magma, volcanic gases, and hot fluids interact continuously with surrounding rock. Unlike volcanoes fed by a simple vertical conduit, Campi Flegrei possesses an intricate network of reservoirs, fractures, and hydrothermal systems that evolve over time. Pressure may build in one location before migrating elsewhere. Hot fluids may weaken rock long before fresh magma approaches the surface. Gas released from cooling magma can travel independently through cracks, altering temperatures and chemistry far above. Understanding such a system has challenged generations of volcanologists because no single measurement tells the entire story. An increase in earthquakes may indicate rising pressure, but similar seismic activity can also result from movement of heated groundwater. Ground uplift often reflects expanding underground reservoirs, yet fluids alone can sometimes produce comparable deformation without requiring magma to move significantly upward. Changes in volcanic gases may reveal fresh magma entering the system, though chemical reactions occurring within hydrothermal reservoirs can also modify those gases before they reach the surface. Every signal must therefore be interpreted alongside countless others. That challenge became unmistakably clear during the middle of the 20th century. Until the early 1950s, Campi Flegrei appeared relatively quiet compared with many active volcanoes around the world. While geothermal activity persisted, the surrounding communities experienced no obvious indication that the volcanic system was entering a prolonged period of unrest. Then instruments detected something unexpected. The land around Pozzuoli, one of the principal towns inside the caldera, began rising. At first, the movement appeared modest. Most residents noticed little or nothing unusual. Buildings remained standing, roads functioned normally. Daily life continued uninterrupted. Scientists, however, recognized that vertical land movement inside a volcanic caldera deserved careful attention. The phenomenon, known as bradyseism, describes the slow uplift and subsidence of Earth's surface over extended periods. Campi Flegrei had experienced bradyseism before. Ancient Roman structures preserved evidence that the coastline had repeatedly risen and fallen over many centuries. Marble columns at the Temple of Serapis displayed rows of marine mollusk boreholes several feet above present sea level, proving that the building had spent long intervals partially submerged before later emerging again. Those ancient scars served as geological records far older than modern scientific instruments. The renewed uplift beginning during the 1950s therefore suggested that another cycle had started. Year after year, survey measurements confirmed that the surface continued changing elevation. Though the annual movement remained relatively small, its cumulative effect became impossible to ignore. Harbors required adjustments. Coastal infrastructure reflected changing relationships with sea level. Precise leveling surveys documented deformation extending across much of the caldera. The Earth was slowly breathing. Unlike tectonic uplift associated with mountain building, bradyseism at Campi Flegrei occurs because pressure changes develop beneath the caldera. Magma, volcanic gases, hydrothermal fluids, or combinations of these processes can inflate underground reservoirs, gently lifting the surface. When pressure decreases, the land may gradually sink again. Yet determining exactly which mechanism dominates during any particular episode remains remarkably difficult. As monitoring techniques improved throughout the 20th century, researchers assembled increasingly detailed records of deformation. They combined leveling surveys with satellite observations, seismic networks, gas measurements, gravity studies, and geochemical analyses. Piece by piece, a far more complicated picture emerged. Campi Flegrei was not simply rising once before returning to equilibrium. Instead, it appeared to experience repeated pulses of unrest. Some periods featured accelerated uplift accompanied by increased earthquake activity. Others showed slower deformation but continued gas emissions. At times, the surface stabilized temporarily before beginning another upward phase. Rather than ending, the process seemed to pause only long enough before resuming again. For nearby communities, these changes remained largely invisible. For scientists, they represented one of the world's longest continuously observed episodes of volcanic unrest. The significance of these observations grew dramatically during the early 1970s. After years of comparatively gradual uplift, deformation accelerated noticeably around Pozzuoli. Buildings developed cracks, streets required maintenance, harbor facilities experienced measurable elevation changes. Residents who had scarcely considered the volcano beneath their feet found themselves living amid increasingly visible evidence that the landscape itself was moving. Earthquake activity intensified alongside the uplift. Most of the earthquakes remained relatively small, yet their frequency increased enough to attract widespread attention. Swarms rather than isolated events became a defining characteristic of the unrest. Instead of one large earthquake releasing accumulated stress, hundreds of smaller earthquakes occurred over weeks and months as rocks fractured under changing underground pressure. Each fracture represented a tiny adjustment inside the volcanic system. Scientists expanded monitoring efforts, recognizing that Campi Flegrei had entered a phase unlike anything previously documented with modern instruments. By this time, volcanology itself was advancing rapidly. New seismic techniques allowed researchers to estimate earthquake depths with increasing precision. Geodetic measurements became more accurate. Laboratory analysis of volcanic gases improved. Computers enabled increasingly sophisticated models describing underground pressure sources. Campi Flegrei became both a scientific challenge and a natural laboratory. Every measurement raised new questions. Was magma ascending toward the surface? Were heated groundwater reservoirs expanding instead? Had volcanic gases become trapped beneath impermeable rock? Or were several processes occurring simultaneously? No single explanation accounted for every observation. Even as researchers debated competing interpretations, another historical reminder lingered in the background. Campi Flegrei had erupted before, and not merely in prehistoric times. Its most recent eruption occurred during the Renaissance. In the year 1538, following days of intense earthquakes and rapid ground deformation, a new volcanic cone called Monte Nuovo emerged near the town of Pozzuoli. Within only a matter of days, explosions built an entirely new hill approximately 433 feet, or about 132 meters high. Ash blanketed nearby communities while lava and pyroclastic material reshaped the surrounding landscape. The eruption eventually ended, leaving Monte Nuovo standing as the youngest volcano in mainland Europe. Its formation demonstrated an unsettling reality. Campi Flegrei did not require thousands of years to create a new volcanic vent. It had accomplished exactly that within recorded human history. As monitoring networks continued expanding during the decades that followed, every new earthquake, every centimeter of uplift, every change in volcanic gas composition inevitably invited comparison with the events that preceded the formation of Monte Nuovo. Scientists understood that history never repeats itself in precisely the same way. Every volcanic episode follows its own sequence of events. Yet history also provides the only direct evidence of what a volcanic system has proven capable of doing before. That reality explains why Campi Flegrei commands extraordinary scientific attention today. It is not merely an ancient volcano preserving memories of distant eruptions. It is a living volcanic system that has spent nearly 3/4 of a century displaying intermittent but persistent signs of unrest, producing one of the longest and most intensively monitored volcanic crises ever documented. The deeper researchers looked, the more they realized that these warning signs were not isolated events separated by decades of inactivity. They appeared connected, forming chapters of a single evolving process whose ending remained unwritten, even as millions continued living directly above one of the most complex volcanic systems on Earth. By the early 1980s, the pace of change left little room for complacency. Measurements that had once been discussed mainly within scientific circles were now becoming impossible for nearby communities to ignore. Campi Flegrei entered one of its most dramatic periods of unrest since modern monitoring had begun. The slow breathing of the caldera accelerated into a powerful inflation episode that reshaped both the landscape and the way volcanologists understood large volcanic systems. Between the early 1980s and the middle of that decade, the town of Pozzuoli experienced one of the fastest episodes of uplift ever recorded at the caldera. Streets that had remained level for generations gradually warped. Buildings developed widening cracks, water and sewer lines fractured as the land shifted beneath them. Harbor facilities no longer aligned with previous sea levels, forcing costly adjustments to maritime infrastructure. The cumulative uplift reached approximately 6 feet, or nearly 1.8 meters, over only a few years. Although that amount may appear modest compared with the height of mountains or cliffs, achieving such vertical movement across a broad urban landscape represents an extraordinary geological event. Entire neighborhoods rose together as pressure built beneath the caldera. The earthquakes intensified as well. Thousands of seismic events were recorded. Most were too small to cause significant structural damage individually, yet together they revealed an underground system continually adjusting to changing stresses. Every earthquake represented rock breaking somewhere beneath the surface, releasing energy as pressure redistributed through fractures already weakened by heat and volcanic fluids. Residents described hearing deep rumbling sounds before feeling sharp jolts. Sleep became difficult as earthquake swarms continued day after day. Even relatively minor earthquakes gained psychological weight because nobody knew whether they represented the beginning of something much larger. Authorities faced an unprecedented challenge. No eruption had begun, yet the signs of unrest were too significant to dismiss. Public safety required decisions based on incomplete information, balancing the enormous disruption of evacuation against the uncertainty surrounding volcanic behavior. Ultimately, approximately 40,000 residents were temporarily relocated from the historic center of Pozzuoli. The decision reflected not only concern over the volcano itself, but also the vulnerability of buildings repeatedly shaken by earthquakes and slowly distorted by uplift. Then something unexpected occurred. Rather than culminating in an eruption, the intense inflation gradually slowed. The earthquakes became less frequent. Surface uplift stabilized before transitioning into a period of slow subsidence. during which parts of the caldera gently settled once again. For many observers, the apparent crisis had ended. For scientists, however, the absence of an eruption created an even more difficult question. Why had the volcano produced years of escalating unrest only to stop? Traditional volcanic models often assumed that steadily increasing pressure would eventually force magma to the surface. Campi Flegrei had instead demonstrated that a volcanic system could experience dramatic deformation without progressing directly into an eruption. That realization fundamentally changed volcanic hazard assessment around the world. Researchers increasingly recognized that volcanic systems may release pressure in several different ways. Some episodes end with magma reaching the surface. Others conclude after underground fractures allow gases and fluids to redistribute pressure internally. In certain cases, the surrounding crust temporarily accommodates the stress before another cycle begins years later. Campi Flegrei appeared capable of all these behaviors. The decades following the 1980s therefore became an era of relentless observation. Monitoring networks expanded into one of the most sophisticated volcanic surveillance systems on Earth. Continuous global positioning system stations measured ground movement with extraordinary precision. Satellite radar interferometry allowed scientists to compare repeated images of the same landscape, detecting deformation measured in fractions of an inch or mere millimeters. Dense arrays of seismometers captured even the smallest earthquakes. Gas monitoring stations sampled emissions continuously, while gravity measurements helped estimate changes in underground mass distribution. Every instrument watched a different piece of the puzzle. The challenge lay in combining those observations into a coherent picture. As technology improved, another important pattern gradually emerged. The unrest was not occurring randomly. Instead, deformation, earthquakes, and gas emissions repeatedly clustered in similar areas within the caldera. Many earthquakes originated beneath Pozzuoli and the Solfatara Picciarelli geothermal region, suggesting that pressure repeatedly concentrated within particular sections of the underground plumbing system. Gas emissions offered equally important clues. Carbon dioxide remained one of the dominant volcanic gases escaping through fumaroles. Unlike sulfur-rich emissions, which often dissolve more readily into groundwater, carbon dioxide can travel efficiently through deep fractures. Rising concentrations therefore attracted considerable scientific attention, because they may indicate increasing transfer of magmatic gases from deeper reservoirs. Researchers also monitored changes in helium isotopes. Helium exists in several forms, and the relative abundance of these isotopes can help distinguish gases originating deep within Earth's mantle from those produced primarily within the crust. Shifts in helium signatures suggested that fresh magmatic contributions periodically entered the hydrothermal system, although exactly how much new magma was involved remained the subject of continuing research. Temperature measurements revealed additional complexity. Fumaroles at Picciarelli became progressively hotter over time. Steam vents intensified. Gas discharge increased. Mud pools expanded and contracted as underground water interacted with rising heat. None of these changes alone proved that an eruption was approaching, but together they demonstrated that the volcanic system remained remarkably active despite the absence of surface lava. Meanwhile, the Earth continued rising. After a comparatively quieter interval lasting several years, uplift resumed during the early 21st century. Initially, the movement progressed slowly, only a few fractions of an inch each year. Gradually, however, deformation accelerated once again. By the second decade of the century, satellite observations confirmed that Campi Flegrei had re-entered a sustained inflation phase. Then came another turning point. Beginning around the early 2020s, the rate of uplift increased significantly. Ground that had already experienced decades of intermittent movement climbed even faster. By the middle of the decade, cumulative uplift relative to the low point following the 1980s exceeded more than 4 feet, or roughly 1.3 meters, in parts of the caldera. The earthquakes returned in growing numbers. Seismic swarms became increasingly common. Hundreds of earthquakes sometimes occurred within only a few days. Most remained relatively weak, yet their sheer frequency underscored that stress was continuing to accumulate beneath the caldera. Some earthquakes reached magnitudes large enough to be widely felt across Naples and neighboring communities. Residents reported furniture shaking, windows rattling, and walls vibrating during nighttime events. Schools conducted emergency drills. Civil protection authorities reviewed evacuation procedures. Public concern rose alongside scientific interest. Despite these developments, volcanologists repeatedly emphasized an important distinction. Increasing unrest does not automatically mean an eruption is imminent. Volcanoes are capable of prolonged periods of elevated activity lasting years or even decades. Predicting exactly when magma will reach the surface remains among the greatest challenges in earth science. That uncertainty became the focus of a major international research effort, culminating in a comprehensive study published in the journal Communications, Earth, and Environment. Drawing upon nearly 75 years of observations, researchers examined whether the repeated episodes of unrest shared a common underlying mechanism. Rather than treating each inflation episode as an isolated event, they analyzed the entire record as one continuous evolutionary process. Their findings painted a compelling picture. Instead of repeatedly returning to its original condition after each crisis, the crust beneath Campi Flegrei appears to have undergone progressive weakening over decades. Every episode of uplift and seismic activity may have permanently altered the surrounding rock, creating new fractures while reopening older ones. As these weaknesses accumulated, the crust became increasingly susceptible to deformation even under comparable pressure conditions. In simple terms, the volcanic system may now respond differently than it did 70 years ago because the rocks themselves have changed. Repeated stressing has consequences. Imagine bending a metal wire only once. It usually springs back toward its original shape. Bend that same wire repeatedly over many years, however, and microscopic damage accumulates until the metal weakens. Although volcanic rock behaves differently from metal, repeated cycles of pressure can likewise alter its mechanical properties. The researchers propose that Campi Flegrei may be approaching what engineers describe as a critical state, one in which progressively weakened rock requires less additional stress before fracturing. Importantly, this does not mean that an eruption has become inevitable. Instead, it means future unrest may produce stronger responses than comparable pressure increases generated decades earlier. The study also explored the possibility that continuing magma recharge beneath the caldera has supplied fresh heat and volcanic gases into the hydrothermal system over many decades. As these gases migrate upward, they increase pore pressure within fractures while heating surrounding groundwater. The combined effects can promote additional deformation and earthquake activity without necessarily requiring magma to rise directly toward the surface. That interpretation helps explain why Campi Flegrei has remained restless for so long. Rather than one short-lived volcanic crisis, scientists increasingly view the past 75 years as a prolonged evolution of an active magmatic system whose internal plumbing continues to reorganize beneath one of Europe's most densely populated metropolitan regions. Yet even after decades of monitoring, one question still overshadowed every scientific discussion. If the warning signs had persisted for nearly 3/4 of a century, what would finally determine whether the unrest faded once again, or whether Campi Flegrei eventually followed the path that had created Monte Nuovo nearly 5 centuries earlier?